Hi, I would like to talk to you about cumulative and non-cumulative errors in control of motors or of robot position. And this is kind of an important thing when you try to do several moves in a series and in the end you want to know where your robot is. The thing is, I have seen quite a few tutorials online that show you a solution for a single move, and they don't discuss the issue of errors. A motor, Lego motor, real motor, any kind of motor does not stop on a dime. It has a limited positioning accuracy. It will overshoot, undershoot after each move. And this is an error you have to live with. You have to design your robot, your algorithm of control, to live with the fact that each single positioning move has a certain destination error. The motor will not stop where you actually wanted it to stop. It will be a few degrees over or a few degrees under. But you have to take care to make sure that those errors, they do not accumulate over time. Let's take, for example, a simple move, quarter of turn of a motor. If I just execute it, well, the motor moved a quarter of a turn. If I execute it again moved a quarter of a turn. Now, am I half a turn further than I was? Or did the error of position after first move and the second move add up? Let's try. Let's check it. I will reset the relative position. 89, 180 should be 1 degree under, 270 should be 1 degree under, 360 1 degree under. Each time it is 1 degree under where it should be, but each time it moves close to the target position. Let's make an experiment. Let's do it several times. Let's reset the position. Go to the reference position with this little line pointing straight up, and then let's do it 16 times. 16 times quarter of a turn should do four full turns. Make a short pause after each move so that the motor actually has time to stop and really rest, so that we can see that it rested. So let's see if it will end up again at 360 degrees or 0 degrees or close to it. Let's check the absolute position, and we are at 0. So it actually worked. Now, if we look closely, and it will help us if we pause for a little bit more time after each turn, after each move, it again stops short of 90, 180, 270, 360. And each time the error is about 1 degree, but they do not add up. Now, let's do one more step, exactly this one. Now, it should not make any difference. Right now, the position should go only 0, 90, 0, 90, 0, 90, 0, 90. Okay, let's reset it after the pause so that we can see it hitting 90 or not hitting 90 actually. And let's see if it will work. It somehow no longer does. Each time the move is a bit shorter than 90 degrees, but now the errors add up. It no longer goes to 90, it no longer hits 180, it no longer hits 270, and it stops short of 360 degrees. What happened? Well, as you know, the motor does not stop on a dime. There is an error in positioning. But the hub keeps track internally of where the motor should be. So when you give it a command of moving a quarter of a turn, it does not look on where the shaft actually is, but what the internal counter tells it where the shaft should be. So the change of position, of target position, is applied to the stored and remembered location of where the shaft should be. So if in the last move it undershot by 5 degrees or overshot by 5 degrees, it doesn't matter, because the hub knows where the shaft should have been, should have ended after the last move. It adds 90 degrees to this set point and tries to move the motor to the new set point. It will again undershoot or overshoot, but it still doesn't matter as long as your robot is insensitive to this small error, because after each step it will calculate the new set point position and it will completely ignore where the shaft is. Even if I move the shaft a little right now, without this step here, if I move the shaft a little between the steps, within the slack of the gears, it would still not throw the position sensor, the position control off. But once we introduce this reset here, this reset resets not only the position, the indicated position of the motor, it also resets the internally stored position, which means right now, after each such reset, we actually tell the controller the motor is where it should be. It is no longer in under or overshoot position, it is right now where it should be. So if it stopped 1 degree short, we now tell it we stopped where it should have. This memory of this being 1 degree or 5 degrees short or 1 to 3 degrees over, this memory gets lost with each reset of the internal position. Now, we can emulate this operation by building a program like this. Okay, we move the motor again to the 0 position. We reset the internal position once at the beginning of the program to tell the software, okay, this is where we started, this is where we want it to be. And now we keep internally, for us, in our software, in our program, the motor internal set point. And we set it also to 0. And now we can repeat, say again, 16 times. This is what would normally happen when we did this. It means we change the internal set point by 90 degrees and we let the motor move until the motor position exceeds our internal set point. And we don't care that it will overshoot, because the next step we will modify the internal set point, again not looking at where the motor is, and start moving until it hits the new position. Each time it will overshoot, but they will not add up. And we can test if it's really going to be so. You can even visually see that the motor moves sometimes more than it should. And I especially use the Spike Essential for this, because Spike Essential is executing the code very slowly, which means this comparison, this test, happens relatively seldom, so it misses the target position often. But even after 16 steps, our cumulative error is only 16 degrees. We can see if the error will get bigger if we make it run longer. Each stop is at slightly wrong position. But since we keep track internally where we should have stopped, we can correct this error in the next move. And the next move will again have some error, but those errors will not add up. They will not be cumulative. They will not integrate over several steps. And we should be ready in just a moment. Yeah, and we are again at this 15-degree overshoot. Same after 16 steps, same after 32 steps. This error is there because our position controller is imperfect, but this error does not add up across moves. If we did this, not like I have shown here right now, but if we did this like some tutorials suggest you doing, namely like this, reset your position and move until you exceed the 90 degrees you want to turn, we will see that this error will grow. Even though we move very slowly, we still each time overshoot the position, And since each time we overshoot the position and afterwards we reset the stored angle, every error will be melted into our position, will be welded into our position, and will add up. You can see we are half a turn away from our target position because we lost track of our errors, because each time we've thrown away the memory of the error we have accumulated. So if you see a solution for moving your robot but asks you to reset either your gyro sensor, your yaw position, your yaw angle, your motor position, your relative position, your absolute position, every move, be suspicious, because you will most likely have a problem of cumulative error adding up. And instead of doing it this way, which seems logical but is pretty wrong, go for something like this, either for the yaw or for the motor position. Keep an internal set point, keep memory, do not reset your relative position, do not reset your yaw. If you feel the urge to do so, know that you are going to introduce some cumulative errors. And there are cases where it's okay, but for any kind of FLL activity, you will most likely be losing accuracy, repeatability of your runs if you reset any sort of internal position integrator, cumulative counter during the run. If you do so, you have to really understand what you are losing, what kind of information you are losing, and is it okay in your application. Thank you for your attention and bearing with me.